When dealing with grounding at a power panel, it's crucial to understand the distinct roles of the main ground, control ground, and shield ground. The main ground, typically identified by a green or bare copper wire, serves as the primary connection between the metal enclosure of the power panel and the grounding electrode, such as a grounding rod or cold water pipe. Its primary function is to ensure that fault currents are safely dissipated to the ground, providing a path of least resistance for electricity in the event of a short circuit or other electrical fault. The control ground, often a white wire with a green stripe, establishes a common reference potential for electrical controls and instruments within the system. This ground helps to minimize noise and interference that can disrupt the operation of sensitive electronic equipment. By providing a stable and consistent ground reference, the control ground enhances the accuracy and reliability of control signals. The shield ground, frequently implemented as a foil or braid surrounding cables, connects the shielding of these cables to ground. Its main purpose is to protect against electromagnetic interference or EMI and radio frequency interference or RFI. By grounding the cable shields, unwanted electromagnetic signals are diverted away from the conductors, preventing them from interfering with the intended signals. It's generally recommended to keep the main ground, control ground, and shield ground separate at the power panel. This separation offers several advantages, including ease of troubleshooting and maintenance. When grounds are kept separate, it becomes simpler to isolate and identify the source of grounding issues. If there is a ground loop or other problem, separating the grounds can make it easier to pinpoint the cause and implement corrective measures. To facilitate this separation, it is advisable to install separate ground bars for each type of ground. These ground bars should be constructed from copper or brass, as these materials offer excellent conductivity and corrosion resistance. Furthermore, ensure that the ground bars are UL listed or CSA certified, indicating that they meet established safety standards. Connect the green main ground wire, the white with green stripe control ground wire, and the shield ground wire to their respective ground bars. This dedicated connection scheme ensures proper grounding for each function. There are specific symbols used to represent the different types of grounds in electrical diagrams and schematics. The symbol for the main ground typically consists of a vertical line with a horizontal line at the bottom and a diagonal line through it. The symbol for the control ground is similar, but it includes two horizontal lines above the bottom line. The symbol for the shield ground features a vertical line with a horizontal line at the bottom and a diagonal line through it, followed by a T-shape. Beyond these considerations, ensure that the power panel is properly connected to an effective grounding electrode. This connection is fundamental to the entire grounding system as it provides the ultimate path to ground. Additionally, connect all metal enclosures of electrical equipment to the main ground bar. This practice ensures that any fault currents in the equipment enclosures are safely directed to ground. In a three-phase system, the neutral conductor should be connected to the main ground bar. This connection helps to maintain a stable and balanced system, reducing the risk of voltage imbalances and other issues. Grounding is a critical aspect of electrical safety. By following these guidelines, you can establish a grounding system that protects equipment and personnel from electrical hazards. Firstly, consider the grounding electrode system, which is the foundation of the entire grounding network. The grounding electrode system must comply with local electrical codes and standards. Typically, this system involves driving ground rods into the earth or connecting to a metallic water pipe that is in direct contact with the earth for at least 10 feet. The selection of the appropriate grounding electrode depends on site-specific conditions such as soil resistivity and local regulations. Secondly, the size of the grounding electrode conductor is crucial for safely carrying fault currents. This conductor connects the grounding electrode to the main ground bar in the power panel. The size of the grounding electrode conductor must be sufficient to handle the maximum fault current that the system could experience. Electrical codes provide guidelines and tables to determine the appropriate size based on the size of the service entrance conductors. Thirdly, equipment grounding conductors play a vital role in providing a low impedance path for fault currents to return to the source. These conductors are typically green or bare copper wires and are run along with the circuit conductors to each piece of electrical equipment. The equipment grounding conductors connect the metal enclosures of equipment to the main ground bar in the power panel, ensuring that any fault currents are safely diverted to ground. Fourthly, bonding is another essential aspect of grounding. Bonding involves connecting all non-current carrying metal parts together to create a common ground potential. This includes metal conduits, enclosures, and other metallic structures. Bonding reduces the risk of voltage differences between these parts, which could create a shock hazard. Bonding jumpers are used to connect these parts together, ensuring a continuous and reliable ground path. Fifthly, ground fault circuit interrupters, or GFCIs, provide an additional layer of protection against electrical shock. GFCIs are designed to detect small imbalances in current between the hot and neutral conductors. If an imbalance is detected, indicating that current is leaking to ground, the GFCI will quickly trip the circuit, cutting off the power and preventing a potentially fatal shock. GFCIs are commonly used in areas where there is a risk of contact with water, such as bathrooms, kitchens, and outdoor locations. Sixthly, surge protection devices, or SPD, are used to protect electrical equipment from voltage surges caused by lightning strikes or other electrical disturbances. SPD divert the excess voltage to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the main power panel and at individual equipment locations. Seventhly, regular inspections and maintenance are essential for ensuring the continued effectiveness of the grounding system. This includes visually inspecting grounding conductors, connections, and ground rods for corrosion or damage. Ground resistance testing should also be performed periodically to verify that the grounding system is providing a low impedance path to ground. Eighthly, proper labeling and documentation are important for identifying and understanding the components of the grounding system. Grounding conductors, ground bars, and other grounding equipment should be clearly labeled. Documentation should include diagrams, schematics, and test results. Ninthly, follow local electrical codes and standards, which provide specific requirements for grounding systems based on local conditions and regulations. These codes are designed to ensure the safety and reliability of electrical installations. Tenthly, engage qualified electricians or electrical engineers who have the expertise and experience to design, install, and maintain grounding systems. Attempting to work on grounding systems without proper training and knowledge can be dangerous and may result in serious injury or property damage. In addition to these key considerations, it is important to understand the different types of grounding systems commonly used in electrical installations. Firstly, a solidly grounded system has the neutral point of the transformer or generator directly connected to ground. This type of system provides a low impedance path for fault currents, allowing protective devices to quickly clear faults. Solidly grounded systems are commonly used in industrial and commercial applications. Secondly, impedance grounded systems use a resistor or reactor to limit the amount of ground fault current. This type of system is often used in applications where it is desirable to reduce the magnitude of ground fault currents to minimize equipment damage and arc flash hazards. Thirdly, ungrounded systems do not have a direct connection to ground. In an ungrounded system, a ground fault will not cause a circuit breaker to trip. However, the voltage to ground in the unfaulted phases will increase, potentially leading to insulation failure. Ungrounded systems are sometimes used in critical applications where it is essential to maintain power continuity. Regarding the National Electrical Code, or NEC, several articles specifically address grounding requirements. NEC Article 250 covers grounding and bonding in detail, providing requirements for grounding electrode systems, grounding conductors, equipment grounding, and bonding. It is essential to consult NEC Article 250 when designing and installing grounding systems to ensure compliance with code requirements. NEC Article 310.15 addresses conductor ampacity, including the ampacity of grounding conductors. The ampacity of a grounding conductor must be sufficient to safely carry the maximum fault current that the conductor could experience. NEC Article 408 covers switchboards and panel boards, including requirements for grounding and bonding. Switchboards and panel boards must be properly grounded to ensure the safety of personnel and equipment. Effective grounding is not merely a compliance issue, but a cornerstone of electrical safety and operational reliability. The separation of main, control, and shield grounds, use of approved ground bars, adherence to relevant codes, and consistent maintenance collectively contribute to a robust grounding system. This system mitigates potential hazards, protects sensitive equipment from interference and damage, and ensures the safe and continuous operation of electrical systems. Remember that the primary goal of grounding is to provide a safe path for fault currents, preventing electrical shock and minimizing damage to equipment. By following these guidelines, you can ensure that your electrical systems are properly grounded and protected. When working with electrical systems, always prioritize safety and consult with qualified professionals.